Arg. That was weird. All right. All right, we're back. We are Game 2005. That's Game Physics. That's where we are. We're in the fall 2017 semester here at George Brown. We are week 4, part 1 of our broadcast. We're talking about 1D motion. So this is the first day we're talking about physics. But before we get there, I want to quickly talk about the test that's coming up next week. So again, even though it's a test, I still classify this in terms of an exam because it's like 15% of your final grade. When I see a test that's worth 15% of your final grade or more, it's an exam type. That's what I'm thinking about it. Like I said before, it's going to be on Blackboard. So it's going to be a digital test. So it's not going to be a paper test that you're going to get. However, you're going to be allowed to bring in paper. You will not be able to bring in your own laptops. You'll have to use the machines in front of you in the lab. Okay, so please don't bring out your laptops or anything like that during that day. You're going to have to keep your phone away and all that kind of stuff. For people who have who need accommodations, please see me after class. I want to make sure that you're accommodated. I just want to make sure again who you are. There are people who need that. That's perfectly fine. Calculators are for sure allowed, but not programmable calculators. So don't bring in some kind of crazy mini computer. It won't be allowed to bring in your iPad or your phone for your calculator or anything like that. You will be required to sign in for the test, so I'll have an attendance list. You know, chances are I'll get you to sign in for the first time. And the reason for that is just to make sure that everyone's here and no one missed their test, right? Because I want to, not because I don't know who you are. I know for the most part, I know most of you now at this point. There's some people that I don't know. Yes. It's in the lab. So it won't be during this period. So it's not going to be on the Tuesday at 3:30 to 5:30. It'll be at the other time frame. So it'll be if you're section, I believe 3, that'll be next period between 5:30 and 7:30. So whoever's in this next section on Tuesdays. If you're on the Thursday, it'll be 3:30 and 5:30 respectively. And then what it's going to be is a randomized set of questions that's going to be composed of 2 or 3 different pools of questions. So, for example, I'll ask you some questions about limits. That's one pool. Randomized questions. There'll be a pool around derivatives and a pool around integrals. That's it. That's what your test is on. It's on 3 sections that we've asked for. You know, that we've kind of been studying over the last 3 weeks. Question over here.
Sure. So I cannot bring my exercises.
If it's a programmatic calculus, something you can program, you can put some code into it. If it's a graphing calculator, you're not going to need to graph anything. You're going to do everything by hand if you're going to do anything. So the answer is no. Make it just so it's a scientific calculator, non-programmable. All right? Yes, Emma.
Are these going to be like problem solving, or is it only going to be one problem solving?
There'll be a couple. That's a good question. So there'll be one problem most likely that you're going to be given per section max, right? So if you have limits, you might have one problem limits. You might have one problem on integrals and one problem on derivatives. The rest are going to be literally a multiple choice or fill in the blank, one of those 2, and that says things like, it's going to be this many meters or whatever, and you choose the right one. And the only way you can choose the right one, unless you randomly pick C or something like that, just pick C the whole way down. If you do one of those you could get some points, but the thing is, if you the way it would work is you have to get the right answer. So, and the answers that I'm going to put in there are going to be like within 3 decimal places or 2 decimal. I'll say it on the question. So I'll say the answer here is the best answer. Pick the best answer, right? So that's where it's going to be. Yeah.
So the entire quiz is just going to be multiple choice, and it's not just playing the numbers.
Multiple choice or fill in the blank or true false. One of the 2.
So how big would you say each section is?
Again, it's worth 15%. Even if it was worth 20%, my ratio typically in terms of point value. So I've given you some examples in lab, right? When we were in lab, I kind of said, hey, here's a mark, here's a mark, here's a mark. Well, typically what I do is if it's for every percent of your final mark, it's worth 3 or 4 marks that I give you. So you got to figure that if it's 15%, that means there's probably going to be at least 45 to 60 marks. And if you take that and divide each question between 2 and 4 marks, there you go. That's how many questions they're going to be, right? So I'm not going to, and it's going to vary. I can't give you the exact number because it's going to vary. Everyone's going to have the same points value. So if you have a pool of limits might be worth all of them might be worth 2 points as an example, right? And then there might be some that are application questions that are probably going to be worth 4 points or 5 points. Again, think about the homework you've been given. If I've given you stuff on the slides, that's a good indicator of what you might get if, you know, as an example, with maybe some numbers that are changed. Just being honest with you. So those are the kind of questions you're going to get. You're not going to get something crazy that is like you've never seen before. Typically, also, if your assignment is a good indicator of maybe some of the longer application questions you're going to get. And again, they're not that difficult. Maybe some things are going to be changed from the assignment perspective. But you're going to be given a sheet. So stuff you're going to be given. You're going to be getting a sheet. I'm going to hand out a cheat sheet, okay, on your test. So you're going to get a cheat sheet, the one I've created that's only for the only stuff you need for your tests, right? You're going to hand that back to me at the end, right? So the cheat sheet's going to come back to me. And you're going to get, you can bring in your own scrap paper, which I'm going to look at, right? I don't know. We'll see. Maybe what I'll do is I'll make an announcement and I'll bring in a sheaf of paper and then just take papers. You know, maybe I might do that for you just to keep it. I'm just trying to keep it fair, right? That's all it is. So that, you know, people aren't devious. I have a real devious mind. I can always think about 10 things, 10 ways to cheat. So if I can think about it, I'm sure you guys can think of 20 ways to cheat, right? So not that I'm saying anyone's a cheater, but hey, you know, we all try and do the best we can.
You are saying you're creative.
Sorry?
You are saying you're creative.
I am saying you're creative. Yeah, you guys are gamers. So if anything, it's like this, again, the most difficult program you can be part of. For you to be successful as a game student out in the wild, so to speak, you know, it's like you got to have multidisciplinary kind of skills and abilities. And that means you're probably a creative lot. And I mean, I have to be very careful because, you know, we're all hacks in some ways. And I've been in your shoes. I'm in your shoes, right? I'm still doing my master's, right? So at the end of the day, that when we go through all those steps, you know, I want to try and make it fair for everybody. That's what the whole thing's about. And so I don't want to make it too overwhelming. It's not supposed to be trickery. I'm not going to try and trick you on the test. Okay. It's not going to be hey, what kind of magic trickery is Tom going to pull so that it's really difficult to do the test? That is not the test that I want to make for you. Okay. Same thing for the physics test you're going to get. And same thing for the last test you're going to get. It's going to be all stuff that we've talked about. So again, success. If you're going to attend class, ask questions, make sure you attend your labs, or at least watch the video and attend your labs. One of those two things. You know, I've talked about what the textbooks are. You can get a textbooks on physics. You can look at and do some practice questions on your own. There's tons of opportunities online to do that. I think that's a key way of practicing. Especially if you take some of those questions and those on those sites that I showed you, Symbol Lab as an example. Go up on Symbol Lab and actually, if you go down, you take any question, and then on the bottom there'll be a bunch of other practice questions down there. Try those. Like those are another questions you can kind of go into and practice. Bottom of the lessons, and also online. There's some other practice questions you can do. If you get good with stuff, I mean, you have to practice limits, you have to practice derivatives. Those are the easy ones. The integrals is where you get a little bit more creative, especially that last piece, integration and parts. If I do any of those, there's going to be one question. I know you're going to blow your brains out, Corey. I don't mean to do that, but maybe only one question like that, and the rest, and that'll be worth more than other ones, right? All right. Let's get to this thing. So next week again is the test. I will still do a lecture next week. So even though there's a test, we're still doing 2D motion. So during this period, we're going to do a lecture. I'm going to record it. And then in the following period, right after that, there'll be the test. Okay? So that's how we'll do it, starting off next Tuesday.
I'm sorry, so the test is this week.
Next week, not today, next week, week 5, right? It's actually, if you look at the syllabus online, it tells you when. Yes. Trigonometry might be included as part of physics coming forward, right? I can't really do all the stuff on trigonometry only. It's just a primer to get you going with algebra. That was what it was for that first week. But you're going to see it in physics. You're going to be seeing it everywhere else. I'm going to refer to it when we do this stuff, especially in 2D motion next week. I'm going to say, remember trigonometry, because that's going to be on the test, the following test. Yeah.
So the test is basically limits, derivatives, and integrals.
Yeah, for the most part. Yeah. All right, and then, like I said, take a look at your assignments. Anyone not look at their assignment yet? Hopefully, hopefully everyone's looked at their assignment, right? You got to do your assignment individually, even though it's a group assignment, a pair assignment. Do your assignment individually first. I recommend that. It's going to help you with your understand at least from a problem and concept perspective on the tests. and do your homework. Do those homework, questions that I've given you on the PowerPoint, the back of the PowerPoints, and it should help you out. All right, no more questions about the test? All right, we're going to get to it. Let's talk about physics a little bit. We're going to be talking about motion in one direction today. This is much more relative or relevant to you than some of the stuff we did when we did derivatives and integrals and all that stuff. You'll see this is much more relevant from a game perspective because we're always going to move stuff around, right? We're always moving things around in game, right? So this stuff is important stuff. Okay, we're going to start talking about something called kinematics. How we reflect motion from a physics perspective. So, okay, do we need a physics engine? That's the question, right? And for some games you don't. But when it comes to platformers, any kind of 2v2, two twin stick shooter against someone else in a 2.5D world, any kind of three-dimensional stuff that we do, physics is really, really important. And what we're trying to do here, starting from today, this is the first physics day, is try and get you to program realistic motion. That's what it's all about, right? So how can we make our games look more realistic when it comes to things like lobbing grenades at somebody, at objects falling off of a platform, things falling on your character's head, those kind of things. How do we make that more natural and realistic? And also, we also have to open up with this. You might be making a game now that's, one of these kind of competitive games or the kind of games that we make. But there's also other types of games, like serious games that we do for training. Like some of you may not be going to, work for a big game studio. Maybe you'll work for some enterprise where you make games to train people, like, for example, health and safety games or those kind of things. And so or maybe some of you are going to be doing things like, I'm saying, there's all kinds of possibilities, right? Or maybe you're going to be working in an industry where you're going to be making simulations, like, for example, for some kind of bioinformatics simulation where you're talking about how the eye, you like literally, map out how the eye looks, or some natural simulation with cloth or fire or something like that, or whatever. As we get towards this, as you continue to work with physics, at least starting with this semester, you're going to get better at understanding the natural world. That's what the idea is, right? You're going to try and map the natural world. We're going to try and do that, and with some programming practice as well, mapping the natural world to the stuff that we can program, right? So it's not always easy, and we're going to have some challenges in mind. In the tutorial today, what I'm going to try and do is kick off a Unity thing. We might do a little bit of Unity today, so I'll be prepared for that with basic motion in 2D, that kind of stuff. We'll try and simulate some of those things, and with absolutely no rigid body or any kind of whether it's 2D or 3D. We're not going to use a rigid body to simulate that motion. Okay. So that's the kind of the challenge in this semester. So when we talk about kinematics, it describes motion, right? And one day, I don't know if you guys are going to do any kind of modeling at all. You may not, but some of the things that modelers do, they use inverse kinematics a lot of times with models to give a natural motion to a 3D model that let's say has an armature or bones to move things across a landscape or whatever. So we use physics combined with locomotion to give kind of a natural movement. All right, so different kinds of motion. We got translational motion, right, where we move a car, in this case, across a highway. Rotational motion, we're going to talk about. We're not going to really talk about vibrational motion too much in this class, only maybe from a springs perspective. That's the only kind of maybe vibrational motion we'll talk about. Something that moves back and forth, right? Sorry? Like Spider-Man. That might be, but more from a physics perspective as opposed to an integrals perspective or derivatives. So that's the stuff. So we'll be talking about those things, right? Swinging of a pendulum, that kind of thing at the very most, but not too much vibrational, like mostly in translational and rotational, and mostly in the first sections, all translational physics. How do we move things from here to there? How do we do natural motion? Next week, we're going to be talking about motion in 2D. How we're going to be talking about particle physics more than anything else. We're going to be using the particle model. So this is very interesting. So where, think about a rigid body, right? And it's all rigid body stuff. We're not going to be talking about soft body physics. That's a whole other thing. We're not going to be able to get it totally out of scope for this course. Like, for example, the soft body physics or dynamics of a a drop of water or something crazy like that. We're not going to get that crazy because that is university level work. I'll be honest with you, that's really challenging to do. You might be able to get into that with your physics engine class, but I don't expect that you need to go that far. And for the most part, what are we going to use in real life? We're going to use bullet physics. I'm going to use a physics engine, chances are, right? I might use bullet physics. I might use the physics engine that Unity uses. I might use, for 2D, box 2D physics, right? I might use that. Fizzy.js or whatever. There's all kinds of, whether you're on the web or using C++ or C# or whatever, there's so many physics engines that are out there that are already out there that work. To reinvent the wheel, there has to be a real reason for it. For example, I don't want the whole physics engine. It's too heavy. So I write my own little physics algorithm so that it looks natural motion, right? But I don't want to use a physics engine. Or maybe I'm in a group of programmers that are building a physics engine in the future where I don't want to pay royalties to a physics engine that already exists, right? Because if I pay royalties, that means I gotta take my money and give it to somebody for something they've already pre-built. All right, so we're going to be starting off talking about position. Actually, this is the first function we talked about when we talked about derivatives and limits, right? How do we start with position and we get velocity and acceleration. But in this particular case, when we think about position, think about it because we're thinking about all rigid bodies as a point. Remember going back to the previous slide, think about the particle model, how the of an object is what we're looking at for its motion. I'm not looking at the entire model to figure out the exact, start off with a particle. So everything we look at, whether it's a car, a spaceship, the CN tower, whatever moving across the space, it's a particle for us, right? And we're looking at that exact center of mass, the place where everything kind of is in equilibrium. So if that's the case, when we look at this car model, right, and we kind of talk about, we always start with this idea of a motion in one dimension, right? We have an origin, and in this particular case, the car starts at A and moves to B, right? So we have an origin, an initial position, right? And we have a final position. And because we're moving across the x-axis, you can think of it as x initial, right? And then x final. So xi, we'll make an I, a little subscript of I, and an x, you see?
Yeah, can you turn off the front light?
Turn off the front light. Can you try it over there? One of you guys try it out? Oh, you got a couple guys. Go, both you guys. So maybe one of you guys will figure it out. It's just the front one. Let's see if he's right. Nope. You're wrong. Right? Like I said, you need a couple people. There we go. A couple people figured it out. Yay. Good job, guys. Good work. Good teamwork. So again, you have this idea of because we're traveling on the x-axis, and if we're going to map out a one-dimensional movement across an axis, you're going to move across one axis, x or y. So what kind of movement are we going to be talking about today? Things moving on a solid surface, or things that are falling, things that are being thrown up into the air and then coming back down. Those are the types of movements we can talk about, we can describe in 1D, right? It's across one axis. Or if you're casting something that's into the z coordinate somehow, if you're doing 3D, that is, again, a 1D motion. So if you think about this, starting off at A and going to B, there is initial position and a final position. And what we want to do, we want to get the distance, is take the final position minus the initial position, and then you get the distance, right? That makes sense. Here, as an example, the car moves left. Now notice the car is pointing to the right, but it's moving left from C to D to E to F. And you can see that it has different, almost like we're giving almost like a little time lapse, a little snapshot of where the car is going to be. Now, if we have this kind of motion, and let's just imagine that the car was pointing the other way, you can see that we would say that the car then is slowing down until it stops. Slowing down is another way of saying deceleration, right? It's decelerating instead of accelerating. Speeding up, we're going to talk about acceleration and deceleration. Speeding up is like accelerating. Our velocity, our rate of change of velocity is moving upwards. And when it's slowing down, our rate of change of velocity is going downwards, right? So what ends up happening is we have this acceleration or deceleration. Sometimes we also talk about deceleration as negative acceleration, right? That's a natural way of talking. The negative acceleration of an object is just its deceleration, okay? Just so that we're not confused. Physicists don't like doing that, though. They like talking about acceleration, and then they assign a positive or negative value to it, okay? So again, it starts at a point, and then we move things across in one direction or the other. So when we look at the position time graph for something that's moving around, we see a point. Notice that on the x-axis, that's all we care about, right? And if we looked at this as the x, this is the x-axis in this case, the one that goes up and down, and this bottom axis here is time, we can see that as it's moving across in a positive motion, right, as an example, from a time perspective, so as time ticks towards the right, so it starts with 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds. Then its position would change. The car's position would change, as an example, depending on how fast it was moving and how much time had elapsed. So, by the way, please stop me if I'm going too fast or it's too confusing. So we can actually map the table. Sometimes we'll use tables. Sometimes we'll use graphs. Sometimes we'll use other instruments, basically to describe motion, right? So basically we're trying to make it easy for ourselves to describe what's happening in the real world. Is that a question or, yeah? So, and that's what we're using. That's why these diagrams are here. In this section, and again, starting with physics, this is today the first day, you'll be making lots of diagrams, all right? So part of the thing is, when you look at a diagram, to try and understand or map, make a visual mapping of what's happening in the real world based on maybe a problem question. This is just an example of the same things we looked at in the previous slide, right? Just mapped to a table, right? So if we looked at a table like this, I can map all the points. By the way, for those people who are curious, I know I'm a curious kind of guy. If you look at Desmos, right? I like looking at Desmos a lot because this is, and some of you may be using Desmos for your assignment, which is totally fine. Just make sure you do a screen capture or export, right, for it. If I want to provide a table, right? So if I go here and I go, I want to add a table. Here's a table. I can actually do this. I can actually map X and Y values in a table. So I can start off at, for example, 0 and 30, where 0 is the X-axis and the distance is the Y-axis. So 0 and 30. And then we're going to go to the next part, which is 10 and 52, just to give you an idea of how this works. 10 and 52. And then we're going to go 28, 20 and 38. Right, and a 30 and 0, really quickly here, and 40 and minus 37, and then we're going to go 50 and minus 53, right? So really quickly, I just showed you how to put a table together, but where is this stuff? How come I can't see it? Well, because it's a big. You can see that it's a bunch of points, right? So here's a bunch of points. So you can see how this would map out a kind of curve, and if you would. To kind of connect these points with lines or some kind of curved line, you can see that this maps out a curve. I can actually click on one of these or all of them, and you can see how this maps things out. So really kind of neat, right? The way Desmos works, you can graph it out. And of course, in real life, if you're going to graph it, I would graph multiple points on the same line to make my own graph, right? Why are graphs important for us? Some people hate making graphs, right? Because it helps us visualize what's happening with the motion. Okay, and imagine if it's not time in seconds, but time in frames for you guys, right? I want you to always convert your time in seconds in your mind to times in frames, right? And then you always got to think about how many pixels per frame am I going to move my car? Instead of meters per second, it'll be for us in our mind, think about pixels per frame, right? Because that is going to describe natural motion. You're going to convert stuff. That being said, how many pixels per meter is going to be your scale, right? So if we have a game, maybe our pixels per meter scale is going to be 30. So 30 pixels describe a meter in real life, let's just say. And that can describe the size from a scale perspective of your characters or your platforms or whatever. I'm just using an arbitrary value, 30. Maybe it's going to be 50. Whatever makes sense for you in your game. But you need to kind of map out a scale. When we program together, we need to say, well, you know what? Our scale, our world scale, 1 meter is equal to 30 pixels or 50 pixels. And then from there, once we go down that road, then we're going to be able to map out the same motion with a new scale. All right, so this is what this is here, right? So this is this thing. We can map it out with this. So again, we talked about a few things: pictorial, some way of making a picture, graphical, tabular, or some other mathematical way of doing things. We're going to use some way of expressing what's happening in the real world, right? Okay, and this is kind of the idea, but the goal is kind of some way of mathematically expressing. Right, we might have to use multiple things, multiple representations. Like we have a picture, we also do some graphing, and then we come up with the math after that. And the reason why we do this is to try and break down a problem in its parts or subparts to understand how to do something. And in this course, after week 4, going forward, you will maybe have to use multiple equations or multiple ways of breaking down a problem. It won't be just one thing. That's why I told you the first 3 weeks were just, hey, refresher on algebra and people who've never done derivatives, new derivatives and integrals and that kind of stuff. So it can help you do physics problems. So Corey, you had a question?
Pictorial and graphics on like a chart.
Pictorial might be a picture. So you draw a picture like almost like a wireframe of what the thing looks like. So you actually try and picture it in your mind. Remember I talked about the whole thing with some people in the world, in Asia and in other places, they try and first picture it. If I can picture it, I can solve it. That kind of idea. And I think you should take that kind of concept. So use pictures as much as you can to try and draw out what the problem is as much as possible. All right, so this is the idea. So we always talk about distance, and there's different things. When we talk about moving, we always talk about something called displacement. Okay? Now we're not talking about, when I talk about deltas here, see this big delta here, this Greek symbol? This is the capital delta that I'm looking at right here. There's also a smaller delta, which is what we've seen in derivatives, right? We're not talking about derivatives yet. We're just using delta to say the change. Whenever you see here in your mind delta, it's changes. Actually, we do this in business as well. Tell me about the deltas, right? That's kind of a common saying. Show me the deltas, right? Show me the changes in this particular, from month to month. We're looking at the deltas. Here, we're talking about the change between the initial position. So delta x here talks about the change from the initial position to the final position. So when we talk about that is what we call displacement. Okay, hold on. And then when we talk about units, usually we think about displacement. The natural form when we write displacement in math is the S, capital S, means displacement. It's not a D. D is something else, right? So S is usually the stuff we use for displacement. So delta x, again, displacement can be positive or negative because we talk about how far it's gone and from your initial position, and that could be either on the left-hand side or the right-hand side. So it kind of talks about direction in some ways, right? Where the difference between distance is almost like the absolute value, right, of how far we've moved. That's more of distance doesn't really have a negative value. You can have negative distance, but you can have negative displacement, right? Negative distance is only positive distance, right? Let's talk about this. And by the way, please, if you don't understand that, it's actually quite simple to understand. But we're gonna get into more of a different example here that I want you guys to focus on. Okay, here's an example. Here's distance versus displacement. Here's the example. Basketball court here. And you've got a player that here's the starting position down here, and he runs down the basketball court, down the length of the basketball court, and back. What is his displacement? 0, right? He's gone there and come back. It's relative to your starting position. What is the distance, though, that he's run? He's run there and back. So it's twice the length of the basketball court, right? That's what's happened. So distance and displacement are two different things. And when we talk about that, the reason why I'm bringing this up is because I don't want you to be confused. If I say displacement and if I say distance, you should know the difference, right? Some of the stuff we do today is going to set us up for other days. So there might not be as many questions to kind of handle in tutorial as there are. What I want to handle here is more concepts than anything else. All right, vectors revisited, right? We're going to have vector quantities sometimes in this section and going forward. And we're going to have scalar quantities. So vectors, again, have both magnitude and direction, where scalars are only magnitude, right? Sometimes we want a scalar value as the answer to a question, and sometimes we're looking for a vector, some kind of point in space, right? With a direction. All right. If you're asked to find the average velocity, okay, I want to talk about velocity a little bit, right? Really, when we think about velocity, what is that? It's kind of like speed, but there's a difference between velocity and speed. Yeah, see that? There you go. So if velocity is displacement, displacement has a direction, right? Whereas distance doesn't, right? Distance doesn't have a direction, but velocity has a direction. That's why we use velocity, a velocity direction vector typically, to describe certain things in physics, right? So if you look at velocity over time, so the change in displacement over the change in time, then you have this idea of an average velocity. Why am I saying average velocity? What's the difference between average velocity and instantaneous velocity? Because sometimes what happens is you don't have constant velocity. So maybe I'm driving along on the highway, but how often do you stay the exact same speed at the entire length of the highway? Or even if you're on a street, and you're driving 40 kilometers an hour or 60 kilometers an hour, you may not drive at a consistent rate of speed the whole time. So you have this average rate of speed. So the idea is you're still traveling in meters per second. How many meters per second? But you have a direction, right? And you have the idea of some time that has passed. When we look at average speed, however, it's purely distance over time. So when I talk speed, it's d over t, distance over time. Velocity is not distance over time. Velocity is displacement over time, right? How much have I gone in a direction over time? It's very similar, right? But speed is always I get a scalar value, right? Whereas velocity, I get a vector value, right? And that's the thing that you have to think about in your mind, okay? Both in meters per second, right? That's the good thing. So you can see that speed has no direction, but it's always a positive number because, you're talking about a distance over time. So if you've traveled, a negative distance, how can you travel a negative distance? Again, in real life, not really, right? You can have a negative displacement, right? Which goes in a different direction, but not a negative distance. Negative distance for us would be somehow traveling through time, right? Or going into an alternate universe. We don't express distance or as negative. All right, so again, this idea of average speed and average velocity, let's talk about those two things. So a runner ends at her starting point. So she starts off, she goes around the track and comes back, and then she's back to her starting point, right? Jamie, where are you? She ran, she hurt herself, right? She came back to the starting point, right? And then what's her displacement? The displacement is 0 because she came back to where she started, right? But velocity, as an example, if her displacement is 0, then the velocity is 0 because velocity is based on displacement, not on distance, right? If you start, it's really dependent on the position of where you end up, right? If you think about this, right? However, the distance traveled is not 0, so the speed is not 0 because you've traveled a certain distance over time. So you can say what was Jamie's average rate of speed? You can ask that question because she traveled around the track, right? She actually moved a distance. If I was going to look at Jamie as an example, sorry, Jamie, as a particle in space, right? She actually literally did something. She moved the particle. There was motion, right? So because there was motion, there was distance. And because there's distance, there was speed. Okay, so when we talk velocity and we talk speed, please don't be confused. There's two different things in the physics world. In real life, we might just say, wow, how fast that person was going, right? What does that mean? Usually means speed, not velocity. Velocity is totally different. All right, when we talk about instantaneous velocity, we talk about it at a place on the graph, right? On the position graph. And we've talked about this over the last 3 weeks, right? Instantaneous velocity, how do you get that? You look at your position function, you take the derivative. That's what the answer is, right? But it gives you this idea of a slice on your graph, just like we saw before. So this green line here is the instantaneous velocity, as an example, as it starts off at this particular tangent line to the graph. And as we change the blue lines, show as the delta gets smaller and smaller, the change in time gets smaller and smaller, it comes to meet that that green line, and then we're talking about limits again, right? So instantaneous velocity is really the slope with respect to the position graph. We already talked about slope. Slope is great for 2D motion. Okay, we use y is equal to mx plus b for 2D motion, but not for 3D motion. A negative thing to do. It's always better to use points in space, in three-dimensional space, to connect each other, for us to get the length of a line and the direction of that line, or that line segment in three-dimensional space, because y is equal to mx plus b does not work in three-dimensional space. It just won't. It'll come up with an infinite amount. All right, and this is kind of this describes kind of the equation. So the limit as delta t, so the change in time approaches 0, right, is delta x over delta t, and that's the instantaneous velocity. And again, we talked about that back in derivatives. This is just a recap of what that is. And like it says, instantaneous velocity can be positive, negative, or 0. Why? It's the slope of the line tangent, or the tangent line to the curve. So if the tangent line is going negative, it's going to get a negative value. If it's going positive, you're going to get a positive value. And sometimes you'll get 0 if it's straight up, right? And you're going to see that in some of the graphs, the figures that I have around. Again, instantaneous speed is only the magnitude of the velocity. So we can still get instantaneous speed, but you're going to put those magnitude bars on the right side and the left side of your velocity, right? So if I see, velocity, the velocity vector with a little arrow on the top, and I have 2 bars on the side, that's usually talking about speed. So all I care about is the magnitude of the velocity, not the direction, right? Which means I only care about speed, not velocity. Okay, so velocity, this is good. Velocity and speed indicate instantaneous values then, but average, if I use the word average, it's going to mean the average velocity or the average speed, which means I got to take the initial position and the final position, right? Or the initial velocity and the final velocity to get an average, okay? And how do I get an average of 2 velocities? Divided by 2, right? So that's what I mean by getting an average. All right, so we have some idea of these analysis models, ways of analyzing a solution, right? We want to, again, think about the description. What is the behavior? How can I draw this thing out? How can I map it to my mind so I can take the abstract question that I get and map it to something that's more concrete, right? One of your questions on test number 2 might be, or assignment number 2 might be draw out the model, draw the free body diagram. You're going to get that in probably question number 2, right? Why? Because you are, assignment number 2, or even maybe test number 2. The reason for this is because it's a key skill to understand how things work. All right, so we talked about different analysis models. One of them is the one we're using right now, which is the particle model. There's other ones that we're going to maybe talk about during this semester. But for now, we're looking at the particle model. The ability for us to look at an object as just one particle as opposed to the whole thing. All right, so there's some really interesting different equations that you can use here. So when we talk about a particle under a constant velocity, and here's a little picture of that. So here's a particle, and notice that the velocity bars are exactly equal, right? So that means it's moving at the same rate of speed every single frame. Notice I said frame, not time equals seconds, right? Because that's what's happened. Think about these as time slices. Every time I see that little red line, it's like, that's what's happened in this frame. That's what's happened in this frame. And it's a constant velocity, right? We want to do that. We want to take the, for velocity on the x-axis, so Vx in this case, is really equal to the Vx average, right? Actually, this should be all in the same level here. Vx average should be written differently. And I don't know what happened here because I had this all figured out, but I guess it moved around. So the mathematical representation, right, looks like this. X final then, and let's just put your hand over the left equation, because really what we're saying is take the delta x, whenever we see delta, it means the change in x. The change in all values x is the final position in x minus the initial position over the change in time. So that's displacement again. We're talking about displacement, right? So imagine where we have something that moves, as an example, from position 10 to position 30 on the x-axis. So final 30 minus 10, right? Initial is equal to 20. That's on the top. How fast, how many seconds did it take to move that space, right? Well, that's the change in time. So if it took 2 seconds to move 20 meters, let's say, 20 meters over 2 seconds is 10 meters per second. That would be your velocity, right? The other way to look at it is your x final. You could always, sometimes we have to move the equation around, right? And that's why this is written like this. Sometimes we need to use one form of the equation or another to solve a problem. So in this particular case, x final is equal to x initial plus the velocity in the x direction times the change the change in time, right? Delta t, which you can figure out by saying time initial or time final minus time initial, right? The same exact idea, right? But instead of x final minus x initial, that's what F and I stand for. It's t final minus t initial to find out delta t, right? If you really want to go there. So we can use one or the other sets of equations. Like it says here, a common practice is to let the t initial value be 0, because what we want to do is we want to zero out the initial location, almost like translate it back to the origin to make it easy for us so we can figure out what it's like from the origin to the new position that we're at, right? And if we do that, if t initial, right, t1 initial becomes 0, then we don't have delta time anymore, do we? Right? All we care about is t final, right? So the total time is what we're looking at, right? So, well, because if I translate my object, right, back to the 0 point, right? So let's say, for example, I only care about the time between the second frame and the 8th frame, right? Well, if we consider the second frame, the first frame, we just move it back. We just move it back, right? It doesn't matter how we do it. It's the difference we care about. And then all we care about is the difference, the total time that's elapsed, as opposed to the difference in time from the final frame to the initial frame, right? So this lower equation here becomes more relevant, right? So the final x position, the final position in x, right, is equal to the initial position, whatever that is, right, plus vt. And a lot of times it's just velocity times time, right? Because we try also to translate our position to the origin, our initial position to the origin. So in a one-dimensional perspective, we might start at the origin at time equals 0, right? And then all we need to do to get the final position is take the velocity times the time, and that's your final position, which is what this is saying. So x final here would be the velocity times the time. Now this again is for all constant velocities in the x direction. If it is not a constant velocity, we need to think about it as an average velocity, right? So there's two types of velocities. Now, in our case, okay, for the most part in gaming, it's constant velocity. But sometimes, if you want some kind of natural smooth motion, as an example, an ease in and an ease out of some kind of object, right? To make it more natural looking, so a speed up and then a slow down, you know, then you're going to have an average velocity that you're looking for. All right, and here's the graph that represents the motion of a particle with constant velocity, right? So it's going to be like a straight line graph, right? Because it's constant velocity. Where the y-intercept is the initial position, right? So here's the initial position, right? The t value down here is the time, right? As an example, so you're traveling a distance x over time over t to get your velocity, right? So change in x over change in time is equal to your velocity. All right, how about, though, that's one case. So one case was this ability for a particle to move with constant velocity over time. The other one is, what about a particle under constant speed? That's totally different, right? Well, it's not totally different, but it doesn't talk, velocity and speed are different in that one is displacement and the other one could describe this kind of motion, right? Notice that the displacement from V initial, or sorry, from P initial, let's say, this is the initial position, to P final, the displacement is much shorter than the distance. Notice the distance goes up and down in a curve, right? But meanwhile, the displacement is very close, right? So if I was going to talk about velocity, what's the velocity for me to get from point A, which would be over here, to point B? It might be quicker, right? If I just draw a straight line, right? Might be quicker because the displacement, it's about displacement, compared to the distance that I travel along a path. The distance along a path might be far longer, right? Because I'm traveling around this, right? So for velocity under constant speed, right? We want to talk about the distance traveled, not the straight line from point A to point B, but the distance across maybe a path, right, over time. So it's very similar to velocity, right? But in this case, it's distance and not displacement. Does everyone see that? Difference between distance and displacement. Please don't get mixed up, because then your mind is going to go, I'm looking at a problem question, trying to cut it up to try and understand what I'm saying. And if I say displacement, right, then you know I'm talking about velocity. If I talk distance, right, then I know I'm talking about speed. And if I talk average, you're going to take the, some kind of final value minus the initial value divided by 2. Hang in there, guys. And how about final average acceleration? Okay, we talked about distance and displacement as being different, and velocity and speed as being different. But what about acceleration, right? Well, acceleration must be a vector, because acceleration, my friends, is a derivative of velocity, right? You derive acceleration from velocity, and since velocity is a vector, so too then is acceleration, right? It's not a scalar value that we're looking for. And usually there's a direction associated with it. So when I'm looking at the average acceleration now, I look at the average velocity from the final position from the initial position, and then I take a look at the final time minus the initial time to get myself an idea of what the average acceleration is. Now, this is not the instantaneous acceleration. That's the instantaneous acceleration of constant velocity, right? This is where maybe the velocity is changing, and I want to get the average acceleration, right? An example of this would be, I'm entering a highway, I go on the ramp, I speed up on the ramp, right? I get a certain rate of speed, I stay constant for a while, and then when I come off the highway, I got to decelerate. So I change my my velocity again as I slow down. And if I took the time I entered the highway to the time I left the highway, there would be a difference, or an average velocity, as opposed to a constant velocity. I would not have a constant velocity because I have 3 particular points in time that are different. Time entering the ramp, time on the highway, time off the ramp, right? Okay, so again, units from a measures perspective, acceleration is measured in meters per second squared. And this is important because we want to square the time every time we have something moving under acceleration. We're going to take a break in a few minutes because some of you are just dying, right? But the reason why you got to talk about this stuff is because if I don't, when we get into the more difficult stuff, 2D motion and other motion, then you're going to have real issues. Let's go to 4:30 and then I'll take a short break, okay? All right, so here's instantaneous acceleration. Instantaneous acceleration, if you notice, right? So there's the blue line, there's acceleration, and there's the red line, which is velocity, right? So notice that the velocity starts off as very small, and that the frames, the time or the distance between frames in terms of distance between pixels. Let's say this is pixels, so we have a little particle, and you can see it's getting farther and farther away. Farther and farther away means somehow we're speeding up. We're getting, in order for me to get farther and farther away every single time tick or frame, if you will, right? That means I must be speeding up. In this particular case, I am. You can see that the acceleration stays constant, right? Pretty much, but the velocity is increasing over time. If my velocity is increasing over time, I have acceleration. If my velocity is constant over time, I have 0 acceleration. I'm not accelerating. My velocity is the same, right? Again, velocity and acceleration have this idea of direction. So here's one of the equations we can use. So distance squared over distance times time squared. Well, this isn't really useful, but, and here's the idea of the slope of the velocity time graph is acceleration. We talked about this in calculus, right? Where we talked about how the derivative of velocity, or the instantaneous rate of change of speed, velocity, is the acceleration. And we can use a graphical comparison to change the idea of we looked at this already, the displacement time, which is just position. Position function and displacement function, same in your mind, right? Because we're moving the position of the object, right? So you can see that the displacement or position function is the top one. Then we have the velocity time graph, And then we have the acceleration time graph, and you can see that they all relate at certain points in time. Okay, I'm going to talk about this really briefly. So again, when an object's velocity and acceleration are in the same direction, then the object is speeding up, right? And when they're in the opposite direction, so if I have velocity in one direction, but acceleration in the other direction, when does that happen? When do I have velocity in one direction and acceleration in the other direction? Braking, right? I'm in a rocket ship, right, as an example. And I'm trying, by the way, rocket physics, that's why rocket science, I'm not a rocket scientist, is so difficult, because not only are you slowing down because of the fuel that's leaving your rocket, but your rocket is actually getting lighter, right? So that's why it's rocket science is so difficult, because you have to figure out the difference in mass from time, 0 to time 1, as an example. That's why it's so much more difficult to figure that out. So, but the idea is still the same. If I have some way of sending force out in the opposite direction, I'm going to get a slowdown. So whenever you get a question, like you might get a true-false question on a test that says, is this object speeding up or slowing down, right? If I give you a scenario, and you should be able to say, if the velocity is in a different direction, then you know that the object is slowing down. All right. So this idea that force is proportional to the acceleration. So the more force I get to put something, the more acceleration I got to go, and the faster I want to accelerate, the more force I got to throw into a system. And why this is key is because of Einsteinian motion. If you think about this, right? The reason why Einstein said, hey, we can never travel at the speed of light in a vacuum, because it's going to take infinite amount of force to get us there, right? Because as we approach the speed of light in a vacuum, which is 300,000 meters or kilometers per second, I'll be okay. What happens is mass, this is where the Einsteinian physics comes in, mass apparently goes through a dilation, a change, and becomes infinite. As mass becomes infinite, so too does our force requirements to push it towards the speed of light. So we'll never get to the speed of light with Einsteinian physics. And that's why we use things like hyperspace in movies, we use warp, all that kind of stuff, because we want to find a solution to get from A to B, whether you're using Star Wars or whatever, or the new Star Trek Discovery. Wow, I can talk about that all day. But anyways, at the end of the day, you've got this other motion because you want to move away from regular physics because of this issue, because acceleration and force there's a relation between force and acceleration, and of course mass, which we'll get into later on when we talk Newtonian physics. All right, we talked about negative acceleration. That's okay to say, but scientists hate the idea of deceleration. They don't want to talk about deceleration. They just want to say negative acceleration, right? Deceleration is a dirty word for physicists. They say, no, that's not really clear. Decelerate in what direction? Because remember, we talked about direction, right? Direction. And if we're talking about gravity, what's the deceleration of gravity? That's kind of weird, right? Because gravity is always an acceleration. And so people get messed up. So they just talk about things like in terms of positive and negative. So here's some motion diagrams, and I'm going to stop after this. Remember, we talked about a couple of options. One of them was pictorial, right? I want to draw stuff. So here's an idea where I want to draw a few kinds of a car moving with different motion. One of them at the top speaks about constant velocity. We're going to get there after the break. And then the second one talks about constant acceleration, right, in the direction of its velocity, you can see. And then there's the third case where I'm moving in a certain place, but I'm also decelerating at the same time. The acceleration is in the opposite direction. And what kind of formulas do I need or math to be able to describe this motion? All right, that's what it is. Let's take a short break. Let's take a washroom break or whatever and come back in like 5 or 10 minutes, right? And we'll continue with the second part of this thing. We've only got about as many slides to go. And then in tutorial, what I'll do is I'll go into details about how to map this stuff out. Okay, let's take 5.